So thank you everyone for coming to our tech talk today. We are absolutely delighted and so happy to have our own Kolm, who was here before, but today giving us a talk and on joint modeling. But before I introduce him, let me mention some housekeeping issue. For as always, for CME credit, you must sign in and you must include your emails and credentials. Don't miss our March 1st tech talk with Mumita Bhattacharya from University of Delaware, who is going to talk about another part of the chronic kidney disease project, and basically the risk of hospitalization in our patient, and that's part of my big data project. So I'm very, very excited. So don't miss anything. Also, please note that February 9th Innovative Discovery Series will have a special guest, Dr. Velma Stankovic from Krishna Care, to speak on ongoing issues in kidney transplantation. I think it's kidney month today. Because this month, because we have a lot of presentations about our kidney data. So, as always, please register to help us and prepare. The full schedule is posted on our website, DE-CTR.org. And finally, please don't forget that registration is still open for the ACCEL Community Research Exchange on March 12, 2018. And also, the abstract deadline had been postponed to tomorrow. So if you haven't submitted your abstract yet, you can until tomorrow. The keynote speaker for the event is Dr. Georgia Dunstan, founding director of the National Human Genome Center, based out of Howard University. She's an accomplished speaker on health disparities and genomic research. So that's going to be very, very exciting. So please do not forget to register. So going back to Paul. Paul is now the Director of Biostatistics, MedStar Cardiovascular Research Network. But before going to MedStar, which was in December 2017, he was Professor of Medicine at Thomas Jefferson Medical College in Philadelphia, and also our own Director of Biostatistics at Krishna Care from 2005 to 2007. So we are missing him greatly. Paul has a PhD in psychology and measurements at University of Nebraska-Lincoln, and from his PhD, had a very distinguished academic career. He started his career as assistant professor in statistics at Southern Illinois University of Medicine in Springfield, Illinois, then worked as director of biostatistics in the Eastern Virginia Medical School in Norfolk, Virginia, and he was also the director of research at the Naval Medical Center in Portsmouth. Then in 2002, he moved to Atlanta, where he was Associate Professor of Medicine at Emory University School of Medicine and Director of Biostatistics at the Emory Center for Outcomes Research, led by Dr. Weintraub in the cardiology. And I forgot to say that Paul, in fact, joined Dr. Weintraub at MedStar. He has taught multiple courses in biostatistics from basic level to very advanced level. And he has also a very long list of publications, has been funded as a co-investigator biostatistician in multiple grants, and has been instrumental in the success of many of our grants. So thank you, Paul, for coming back, and we hope you come back often.
Thank you. So this project obviously is part of Claudine's Big Data Project grant. So this is our disclosure here. And so I'll give you sort of the outline here. Claudine's actually going to do the introduction to this. And I'm going to talk about survival analysis, longitudinal analysis, fixed and random effects, and latent variables. That's kind of all sort of information to kind of understand joint modeling. Then we'll talk about the data, the joint models, and the results, conclusions, and then I'll make a few comments. And I just want to say at the beginning, I'll say it again at the end, this is actually a work in progress because there were a lot of issues along the way, and I ran out of time to resolve them all. So, without further ado, I'll let Claudine.
So I'm back at the podium. Yeah. So many of you know that chronic kidney disease is highly prevalent in the US and in Delaware. 1 in 10 American adults have some level of CKD, and in 2015 in Delaware, more than 2,000 patients were in chronic renal replacement therapy for an incidence of 370 patients. These patients, in addition, have multiple comorbid conditions, and unfortunately, they experience a highly fragmented care. And also, they have a high rate of hospitalization, and that's really what we are going to focus, is the rate of hospitalization today. So in 2014, I was fortunate to obtain a big data grant from the ACCEL CTR that we called linking data for kidney care. The specific aims of these grants were first to acquire and integrate information from multiple data sources, create a unified longitudinal description of care for patients with chronic kidney disease. And the second one was to develop models and methods for predicting hospital admission after an outpatient visit in patients with chronic kidney disease. And this is what Mumita Bhattacharya in the March 1st tech talk, that's what she's going to present. And the third aim was to assess transitions of care of children with chronic kidney disease to adult care. This is a big issue in children because many of these children, as they transition, have difficulty in keeping physician appointments and medication regimen, and they also, because they have sometimes some form of cognitive impairment. So the transition from child care, which is a very nurturing, and adult care is sometimes difficult. However, we are not going to talk about this at all today. That will be another technique at some point. So here are our data sources. Our study population was defined from electronic health record, or was drawn from electronic health record from the Nephrology Associates EHR, the Christian Care Transplant Practice, the Nemours Children's Hospital EHR, and our Christian Care Outpatient Medical Group. So that was our study population, all patients with chronic kidney disease. And then these patients were followed up, and we extracted for the follow-up records, we extracted data from the medical group, and also from Christian Care acute care data. So that's our Cerner database, and this defined our outcomes, because the outcomes here were hospitalizations. Other outcomes included first time in dialysis that we got from the United States Renal Disease System, which is a national registry in the United States, including all patients who have end-stage renal disease and get into renal replacement therapy. So patients who start hemodialysis, peritoneal dialysis, transplantation. And we also had social security death index to obtain information about death. And finally, we linked all our records to Medicaid to have a really better idea of resource utilization in the population of patients with Medicaid. So this is just a snapshot that I wanted to show you to illustrate the rate of complications of hospitalizations in these patients. This is an analysis we did for the Nephrology Associates record. So as you see, the rate of hospitalization, and that's the rate to first hospitalization, or at least one, increases as the CKD stage increase. So in pink, we have CKD 3, meaning patients with a GFR, which is an estimate of the kidney function, between 60 and 30. In brown, we have CKD 4, with patients with a lower GFR between 30 and 50. And in red, we have CKD 5, that's patients who have a GFR less than 50. And so what we see here is that the rate of hospitalizations increases as the CKD stage increases, meaning as kidney function really worsens. And that's something that Paul is going to illustrate very well in his analysis. Well, and this
Christian Care data?
This is, yes.
Okay.
Yes. But this is from the Nephrology Associates database, the rate of hospitalization in Christian Care. And this is kind of stable, from year to year. So there is not much improvement. So that's something that we really also want. That's the goal of this project, right? To decrease hospitalizations in these patients. So that's all in terms of background.
So from the statistical standpoint, there are several things that I want to mention here or to talk about, so we're kind of know where, but what pieces we're putting together here. So as the title said, this is called a joint model. It's a joint modeling of longitudinal data and survival data, or time to event analysis. And so what I have here is sort of an illustration of what we mean by time to event. So for this kind of data, you need obviously a start time and you need a stop time, okay, to measure how long a patient survives or how long they're in the study. So you can see different, I don't know if I want to point here or not, I might push something. But so you can see that in time to event analysis, you can have patients start at different time points, and then they're followed also for varying lengths of time. And so, for example, if I can.
Do we have a mouse there?
Is the mouse showing up?
Yeah. Yeah.
Okay. So here's a person. This patient started at this point in time, and then they were followed to this point in time. And so at that point in time, we lost track of them, either through loss to follow-up, maybe they experienced an event they died for some other cause, say, for example. So we call that person a censored observation. So this person that started here and was followed to here, and they experienced whatever the event was that we're interested in, whether it's death, hospitalization, whatever. So that's what we mean by time to event analysis. So, they have a start time, and then the stop time is either when they experience the event of interest, or they're lost to follow up, or for some other reason you don't have any more information past that time. Okay, and then there are examples here of when the study ends at this point. Maybe they experience an event after the study is over with, but that's not counted in the analysis because that you don't have that information. Okay.
All quick questions, just so that I'm anchored. In terms of the definition of start, maybe this was just a model you were just showing. Did the start mean enrolled?
Start could mean enrolled.
The start of what then?
A start of a study. So if it's a randomized trial, the start time can be either when they're enrolled, or maybe if they're doing some procedure, the start time is when they have that procedure, like a PCI or CABG. That's the start time, and then they're followed up after that.
I mean, for this study, what was start?
I can answer that.
Yeah.
So here, if I remember well, what we did is that the start time was the first time they had a GFR less than 60.
I see.
That we had a documented GFR less than 60, and we always had a date.
Gotcha.
And so then from that point on, we're following them until their first hospitalization. Okay. And so I'll mention that at the end. Obviously, you can have more than one hospitalization, but that really complicates the analysis. So we're at this point, we're just doing first hospitalization. Okay. And so from a theoretical standpoint, this is what survival or hazard function is calculated. So it's the probability of surviving longer than a time at some point in time. So the survival function, S of T, is the number of patients surviving longer than T divided by the total number of patients available for analysis at time T. So, and then the hazard function is just the inverse log of the survival function. So if you know one, you can easily calculate the hazard function from the survival, or vice versa. So, and this that's showing up well, but so this is sort of a picture of what we mean by a survival function. So the plot on the left is what we call a survival plot. So that's showing plotting the the probability of surviving up to any particular time point. The graph on the right, that's the hazard, or what we call the cumulative incident function. In other words, that's kind of plotting, sort of, if you kind of think of the turning the survival function upside down, okay, or not right side up or whatever. So it's not exactly that, but you can kind of think of that way. So the graph on the left is plotting survival. The one on the right is plotting the incident of the event. So it kind of depends on how you want to present your data, which particular one you would use. Okay, longitudinal analysis is what is also called repeated measures analysis. In other words, you obtain a value for some variable on the same patient over a period of time. So in this case, our variable here is GFR. So we have GFR being measured at different time points as the patients are being followed. So obviously, from a statistical standpoint, these measurements are correlated and not independent. And so the simplest repeated measures design is probably most people are familiar with, be just a paired t-test, before and after, or pre-post kind of thing. If we have more than two repeated measures, then we do what we call mixed model, mixed effects analysis, or mixed model analysis. By mixed, we have both fixed and random components in the model. And what we mean by a fixed component is you have some components that are exclusive of interest. In other words, they don't. They're the variables of interest. So, for example, if you want to compare PCI versus CABG, or you want to compare treatment A versus treatment B, those would be what we call fixed effects. Random effects are effects that come from a more or less random selection from a universe of possibilities. The patients are always a random effect, because that's like a kind of random, sometimes not random, but it's could be kind of a random selection of patients from a huge population. Hospitals might also be a random effect. If we have data that we've gotten from different hospitals, they would be a random effect, because you can't get data from every hospital in the world. So you have only a select few that you can get data from. So that's what we mean by fixed and random effects. Okay, and then this sort of illustrates the idea here of repeated measures over time. So here we're plotting the mean values of two different groups at different time points. So now that's repeated measures. That looks like. Okay, then the other concept that we need to talk about is what we call a latent variable. And I used here the SF-36, which I think probably a lot of people would be familiar with. It's a questionnaire that measures the well-being of the person, patient, or whatever. And so this is like a questionnaire that the patient fills out, and typically they have questions relating to different areas, and they rate these on some scale, usually a Likert scale, 1 to 5 or 1 to 10. And then you get a total score based on how they answered the items. Well, for different instruments, these items go up to comprise, or are used to comprise, what we call a latent variable. So what that means is that the latent variable isn't something that's directly measured. It's measured by the individual items on the test, but because we can show that these items correlate together in such a way that they make up this latent variable. So in the SF-36, there's two domains, or two latent variables: physical health and mental health. And you have different items that go into making up each latent variable. So you can then show if the items on the test are correlated, relate to the latent variable. You can also then show if the latent variables are related. So that's one a concept that if you have any background in psychometrics, you'd be really. But if not, that's what we mean by a latent variable. It's not a real. It's not the variable that you actually measure directly. In the sense, it's measured indirectly from or assumed from other actual physical measurements or measurements on a test. Okay. Okay. So here is our longitudinal data. So I think this always sort of, at least to me, helps if you actually see how the data's, what the data looks like, so you get an idea of what we're talking about here. So here's longitudinal data. So you see that what we have is the patient over here, their GFR measurement, and the other variables that we're looking at, age, whether they're Medicaid or not, sex and race. And then in the last column, we have the time in months. Okay, so everybody is starting out at month 0, which, as Claudine mentioned, in this case is defined as when the first time that they have a GFR less than 60. And then the next measurement is the time, or the time then is the next time they have a measurement of GFR. So like patient number 3 here has only one GFR value, so their time in months is just 0. That's when it was measured. But patient number 5 here has multiple measurements at their baseline 1.7 months, here, 4.5 months, 6 months, 10 months, so on. So you can see they have a measurement at each of those time points. And sometimes the particular time points which patients are measured at is the same for everybody, but it doesn't have to be. And in this case, it's not. So you can see that the GFR measurement is coming at different time points for different patients. And you can see then that our variables over here, age, Medicaid, female, race, are all fixed effects. They're not changing over time. They're the same from one time point to the next. Now you might say, why is age not time dependent variable? Well, that's a very interesting question because I don't know that I've ever seen age used in an analysis that varies over time. Usually what is in there is their baseline age. In fact, I think I'm the only person I know that ever used analysis where I used age as a time variant changing over time. But it's the most obvious longitudinal piece of data you could have. But probably because of the complexity of the analysis, if you have it changing over time. But most analyses will just take whatever the age is at their baseline and then use that. Is that the question you have?
Yeah, I was just gonna. So the age in this example represents the date the first GFR.
Right. And so in this case, because we're talking about maybe months here, maybe up to a year, it doesn't really matter. But if you have a study that goes on over years, then as a person gets older, that would probably make a difference. In my mind, it should be treated as changing over time. But okay, so let me push ahead here. So here's then what the time to event data looks like. And this is maybe a little more tricky, but we have the same set of patients here. We have their GFR, but now what we have, the way that we set the data up is for each time point, we have a start and a stop. Okay. So let me do patient number 5 first because that's sort of typical here. So we have their first GFR measurement. They start at baseline as time 0, and then the next measurement is at 1.7 months. So that's the stop time for that first interval. Okay. And so then their start time for the next interval is 1.7 months, and then the stop time is 4.3 months when the next measurement occurs. And then whether they're hospitalized or not is just a dichotomous variable. It's a 1, 0. So, oops. So when they are hospitalized, then that gets coded as a 1. So, and because we're just taking time to first hospitalization here, that's their last measurement when they're hospitalized. Yeah.
So the start and stop are you saying the time is when the GFR is over a certain threshold, or any GFR
At the start,
measure?
it's below 60, but after that it can be any value.
It could go up also, because GFR can vary. So
Right.
we established our first start GFR as the first one that was
Below 60. But any then event thereafter is just any time a GFR measure was collected.
How do you take into account the operational definition, such as like a GFR less than 60?
Oh, but that's not. I mean, this is just to illustrate, the longitudinal data. In some of the study, we defined strictly the patients, with GFR less than 60, more than 3 months, and things like that. Here, it just, we took all the patients who had GFR, and we didn't take into account whether they were defined as CKD or CKD, strictly CKD. This is really to illustrate, the methodology.
Okay. So, and the first patient, their number 3 is a little bit different. So they only have one measurement. So their start time and their stop time would both be 0. The statistical software doesn't like a stop time of 0. So for those patients who only had one GFR, I had to go through and change their stop time to something else. So I put in a small number that was at least bigger than 0. So that's why that's their stop time is 1. Okay. So that's what time to event data looks like. Okay. Now, it may take a while to get through this. And I think Claudine has some questions about the slide. So we have 2 different models. We have the longitudinal model, and we have the time to hospitalization model. So this is just typical regression models where, so for GFR, the longitudinal model, we have what I call beta sub L0. So that's the, in statistical terminology, that's the intercept, that's the constant. And I put the L in there so it's for the longitudinal model, so different from the hospitalization model. And then so I'm in this case I'm looking at GFR as a function of time, which is months and months squared, and the months squared is in there because I suspected that GFR over time is not a linear function. It's probably somewhat nonlinear, so that's what the months squared in there is taking into account. It's a function of age, of Medicaid, sex, race. And then at the end of the longitudinal model, I have 2 terms in there, U and months U. Okay, those are terms that we call that we put in there so that we can define the change over time for each patient. Okay, so because that's what we're interested in, is the change over time in GFR, and then how that affects or is related to hospitalization. So the U sub 1 is what we call a random intercept. In other words, we're saying that individual patients can start out at different baseline values of GFR. They're not all starting out at the same GFR value. And then the months U2 there is what we call a random intercept. In other words, what we're saying by that is that the way that GFR changes over time doesn't have to be the same for every patient.
So the second one is what? Because the first one is a random intercept.
Random intercept. In other words, their starting value can be different.
And the second one
is their random, did I say intercept? Random slope, I'm sorry. In other words, in terms of regression, their change over time. So maybe someone has a large increase, maybe somebody else has a smaller increase over time. So we're going to allow that to vary from patient to patient.
And is it do longitudinal models, do they always include, I mean, without talking about the combined models, but do they always include the random intercept and the random
Well,
slope?
if you don't in there, then you assume everybody has the same starting point and everybody has the same slope. Which, for the most things, is probably not the best assumption to make. Okay. So, and then the epsilon at the end, that's the error term. Okay, so the time to hospitalization model then has the same variables in there. So there's a regression coefficient, the beta is associated with each one of those in the time to hospitalization model. But at the end of the model, you see that I have gamma 1, U1, gamma 2, U2. Okay. So here's kind of the tricky part. The gammas, gamma 1 and gamma 2, those are the latent variables. Those are the variables, that's what connects the change in GFR time to hospitalization. So when we do our model and we estimate those coefficients, if those coefficients are statistically different from 0, then we can say that there's some relationship between change in GFR and time to hospitalization. If they're not, if they're statistically 0, then there's no relationship between change in GFR and time to hospitalization. So that's what we mean by joint modeling. And we're using the latent variable as the connection between the two.
Yeah. Would there always be two of those? Two latent variables, or is it?
There's two there because I'm assuming a random intercept and a random slope. If I have just one of them, say like a lot of models are just like a random intercept, and they assume everybody has the same slope, then I'd have just one in there. That issue is going to come up later. Yeah.
In the time to hospitalization model, what is GFR?
GFR, in that case, would be a time-varying covariate. So I'll try and explain the difference, or what that is in relation to the difference at joint modeling.
Oh, because this is not specific to the joint modeling. This is, in general, a time to hospitalization, right? That's how we should do a time to hospitalization.
If you did
survival analysis.
If you just did the survival analysis, then the gamma U and the 1 and the gamma 2 U2 wouldn't be in there. But this is my joint.
Oh, this is your joint.
This is my joint model.
With the term with the beta, that's not the baseline GFR.
Right. That's the intercept in the model. In other words, that's the average. That would be the sort of the average intercept of all patients. But I'm allowing for individual patients to have different intercepts and slopes, different change over time. Okay. Okay, I'll go on to the good stuff. Okay. So in the database, after some, going through and fixing some things, there were almost 11,000 patients with 34,000 observations. So it's a big data set. And half of them were hospitalized.
So it's not a rare event.
Yeah, so it's not a rare event. And then so I have some of the baseline demographics of age and gender, race, and so on. Okay. So what you typically do first is you do each model separately, sort of see what you get. So here's my longitudinal model. Okay. So you can see that most all the terms are statistically significant. The month squared there is statistically significant. So that means that I have nonlinear change over time.
So it really makes sense. Paul and I were discussing this. I mean, when we see a model, I like that even the variables we are not strictly interested in kind of make sense. So, for example, Medicaid patients who have Medicaid have a lower, or there is a decrease in GFR in patients with Medicaid. They are more likely to have a decrease in GFR between 3.5, minus 3.5.
Minus 3.5. So that's why that the signs here are important, but you have to kind of interpret those in light of in the context of what you're looking at. So usually you need the clinical expert to do that. Okay. So that's the longitudinal model. So here's the survival or the time to hospitalization model. So the GFR, age, and Medicaid are significant, race and gender are not. So here what you have, I've changed the regression coefficients to hazard ratios. So what this means is that for every increase in GFR, every 10-unit increase in GFR, there's about a 3% reduction in hospitalization. 3% reduction in the rate of hospitalization.
Which makes sense. That's what we expect.
And then so then for example, like Medicaid, that means that patients that are Medicaid patients are about 1.3 times more likely to be hospitalized than we're not, which I guess also makes sense. And then like for female and race there, you can see that their hazard ratios are near 1. So that's why they're not statistically significant, because that means essentially the same.
So if you go back one slide to, so if I were to look at the race there, saying there's a higher likelihood of having an impaired GFR, but if I combine it with the other slide, not necessarily more likely to be hospitalized.
Right. So there is race is associated with, black is associated with a decrease in GFR, but not associated with a risk of hospitalization.
So then we come to what we're really interested in is the joint model. And so what we're really interested in here is the very bottom one that gives us the whether there's an association between GFR, change in GFR, and time to hospitalization. And so we see that we have a statistically significant inverse relationship between change in GFR and hospitalization. Now, at this point, I'll talk about this kind of at the end. You say, well, what happened to your other? Shouldn't you have 2 terms in there? Well, yeah, but it didn't work out to have both the random intercepts, random slopes. I'll mention that. I'll talk about that again at the end. So what this is saying is that there's then an inverse relationship between change in GFR and hospitalization.
The only thing is here you have, that's not the association, the yellow highlighting is not a hazard ratio, right? I mean, it's a regression coefficient.
Right, the top ones there are the ones for change in GFR. So those are regression coefficients. I changed those for the survival. I changed those to hazard ratios.
But the yellow one,
The yellow one is actually
the regression.
the regression coefficient. So that's why I highlighted this, separated out. So then, so then, what we want to do is try and figure out a way to be able to visualize this, because I can say, well, we have a statistically significant inverse relationship, but so what does that relationship look like? Which is not easy to do in joint modeling, but I can use the model to get a predicted GFR and a predicted hazard for each patient at their time point. And then so what I did, I took those predicted values and I took an average for each month over the time period and plotted those. And that's what this plot is. So this plot, you have to see there's, when you plot two different things on the same graph, it's sometimes hard to keep track of what's what. But on the left axis is the hazard rate, which I've expressed as percent, and on the right vertical axis is GFR. So you can see that what's happening here, as GFR increases, the hazard for hospitalization is going down.
But,
so that's our inverse relationship.
is it the change in GFR here,
Yes.
or the absolute GFR?
That's a change. So that's why we're doing the joint modeling, which is what the difference is between time varying covariance. In joint modeling, we're assessing the change in GFR as it relates to hospitalization. If you do a time varying covariate, that's just the covariate if you have the value of GFR at each time point.
But what is plotted here is not the change, right? Because I mean, it looks like they are they are absolute GFRs. What you plotted on the y-axis on the right.
Yes, that's the GFR for each month, the average GFR for each month. So I thought this is probably the best way to visualize what's going on, because it's like I say, it's, you know, if you just look at the regression coefficient, you can say, well, yes, it's significant, but what does the relationship actually look like? And so you can see that over time here, GFR increases, but then after about 2 years, it starts to decrease again on average. And then the hazard rate for hospitalization decreases, and then about 24 months, it sort of levels out. So as I understand it, then that's fairly consistent with what you thought we would get, or what the relationship would be.
Except, I mean, I would have thought that the hazard rate would increase, you know, on the far right, because when the GFR decreases.
Yeah. So doing it, just taking the average, and then the smooth lines are just smoothing out the averages there. But it's right. It's not doing that. You have to remember also, as you go further on in time, you have fewer and fewer patients that are in that calculation. So as you can see, when you get out to the end, there's only a couple people left. Couple patients left, so that's why you get the weird big jumps in the mean values. Okay, so we can conclude then that GFR increases as GFR increases, the hazard rate decreases at least up to about 2 years from the baseline, which is when their first GFR was or a GFR was less than 60. And remember that these are adjusted for age, sex, race, and Medicaid status. So if we wanted to look at whether there was because some of those were statistically significant, might want to look at sort of the subgroups. So like, is there a difference between males and females? And so then we'd have to look at interactions in which, really Okay, so let me make some comments about this. So in doing this joint modeling, it's often the case that your model will crash, fail. It doesn't, in statistical terms, we call that the maximum likelihood estimation algorithm fails to converge. I won't go into what that means, but basically what it is, it's not working. You get an error message and you have no idea what happened. So there's several things that happened. Actually, when I started running this, it failed a lot of times. So one of the things that I had to do is I had to change from the semi-parametric Cox model to a parametric exponential model. That worked. Okay. When you do maximum likelihood estimation, you're doing calculus, you're doing integration. So there's different methods of doing that, so you can change those. Interestingly, Stata software has in their manual has a whole chapter on what to do if maximum likelihood algorithm fails. I tried a lot of them didn't. So one of the things that you may have to do also is you might have to simplify your model. And I had to do that. I had to drop the random slope term from the model to get it to. Now, does that have any effect on conclusions? Well, it might. And so one of the things that you can do in this, as well as model missing data, we didn't have any missing data. And then the other issue is that GFR is not normally distributed, which is usually an assumption you make about a continuous variable that's normally distributed. GFR is highly left skewed. In other words, it kind of looks like this. But it would be good to model it just to see. The thing is, with so many patients, that may not make any difference. Sometimes when you have big data, the assumption of normality, may not really matter. You've got so many patients. So those are some of the things that I kind of was thinking about when I ran out of time, when I left Christina. So hopefully we can keep going with this and kind of explore this some more and also look at multiple hospitalization rather than just the first hospitalization. I have several references here. If anyone's interested too in looking at those. Let's see which one was it. The ones by Sprungdal and Robin Hesse. Those are really good. Those basically show you how to model anything you want. Of course, whether it works or not is another question. Model a lot of things and model a lot of things simultaneously. So anyway, thank you for your time. It's good to be back. Good to see everyone again. Hope that maybe I can be back in the future to once maybe if we get more runs here that we can get to work, we can make another presentation. So thank you.
Great.
Thank you.
Right there. So how would we translate clinical?
I think it's easier to visualize that when GFR decreases, the rate of hospitalization. So what you want is to try to keep the patient stable at the same GFR. Try not to and try to avoid drops in GFR, which could be a consequence of acute injury or too many non-steroidal anti-inflammatory or dehydration. And this is well known. I mean, that's not nothing new. You really want to do as much as possible to keep the patients at high GFR and avoid. I mean, what is really interesting, that's really a methodological illustration of what we can do with this type of model. I think when we can think a little through this a little more, what type of information does it bring, in addition to just traditional, for us, traditional Cox model. And I think this change in GFR is really the key of, and that's something which is, I think, pretty new.
So what I don't know is, I was imagining myself as a clinic physician, and I have a panel of maybe 3,000 patients. Obviously, some little software gadget that tells me the median and mean GFR of my panel. And if I am able to, I'm not going to wait till they're 60. I'm going to jump on them earlier than that. But it would be interesting if I could translate that intervention into cost avoidance, things of that nature. Because then I can advocate for supported systems to drive that in. That's what's going through my mind from an operational standpoint, and how to create an application with this knowledge. Because you have a Christiana care-based perspective. You're right, the relationships are well understood, but it's nice when you have a snapshot of your own system. And then you can say, all right, if we intervene at 80, we can actually, and keep the distance, and increase the distance to 60 by, I don't know, whatever time period, whatever. There's this level of benefit. And by the way, these are the best practices to increase that distance. And then I can make sure that there's a standard that can implement it, because the clinic docs are not nephrologists. So there's some variation in terms of how they would approach it. And there may be opportunities. I mean, that's just me off the cuff reflecting on how to operationalize this insight.
Maybe something like, and something would be interesting is to calculate the number of hospitalizations avoided by change of GFR.
Yes, because one of the because that would help with CareLink. Because what you're trying to figure out when you have resource constraints is where to apply them to get the most benefit. They've already stated CKD patients are a major reason for recidivism. You know this. ICHOM is actually, I think they have a chronic kidney thing. So from a global health perspective. So if we have opportunities to target, and we may find that there are a lot of benefits with a very targeted, narrow intervention that can be understood, and you can have an alert in the EHR. If GFR is this, suggested actions, potentially. Because when you have 3,000 patients in your panel, you obviously need, what you're relying on is the patient to show up for their visit to figure out what this is. And then there's a delay in that too. So if you have some type of opportunity using algorithms to select out of that 3,000, that, by the way, 3,000 for one physician. So if you have several physicians with 3,000, you can see how you get something meaningful. That's all. But Paul, here's good news. I actually understood what you said.
So then I have a question. So what do you think? What does it bring in addition to what you showed before, the time series? Remember this analysis of time series with the
Oh, okay. So what we could so basically this is what I've created here is our time series. So we could take just these data, the time series data, and we could do time series analysis. In other words, we could see if these two are related. In other words, we do what we call a cross-correlation analysis. Whether one causes the other, one leads the other, or lags.
So what is the best method then? I mean, if we wanted to look at this information, the change in GFR and retrospective.
Well, basically this analysis just tells us there's an association. If we did the time series analysis, then we could, in a sense, begin to get a cause and effect. In other words, what the thinking would be that the GFR should lead hospitalization. In other words, change in GFR is what's driving hospitalization. That's what the time series would at least partially get at that. So that's awesome. Could do.
I guess in the time series you cannot use covariates unless you do stratification. So that's an advantage here.
Yes. So these are adjusted for age, race, sex, and Medicaid. So if you wanted to look at it without any adjustment, then we'd have to run it without the covariates in there, recalculate the predicted GFR and hazard patient, and see what that looks like. So in one sense, if you do a time series with these, it is the covariates are already in the values, predicted values here. So if we took one or more of them out, it might look different. That's kind of the disadvantage of time series. Then you want to kind of sort through all your covariates, then you have to do a lot of them. Thank you again.